Hi everyone. So in this video I was asked to go through some examples of finding the integrals of trig functions that involve some powers. I'll start by saying I remember even when I was a specialist math student these problems drove me crazy because I would sort of stare at them and just not knowing what to substitute and when to substitute different values. And it still happens a little bit. Sometimes I can go with one of these questions and it doesn't work out, or I'll discover later on that there was a much easier way. But there are a couple of tricks that I do use to help me with these problems. So the first thing is I am going to look at two different types of problems. And what I start with is I look at whether the trig function is even or odd powered. So my examples here, I'm going to say this first example is an even powered trig function, and my second example is an odd powered trig function, because if I put a cos squared and a cos cubed, and a sine cubed, that makes a power of 5, so that's an odd powered trig function. What I do with that odd and even powered is if I have an even power, then my method is to use a double angle formula to help me integrate. And if I have an odd power, then my method is to always use substitution. And often I'll end up using the trig identity cos squared plus sine squared equals 1 as part of that odd powered function as well. So let's actually jump into these two examples and we'll have a look at how I'm going to tackle each of these problems. And we'll start with example 1. So for example 1, first thing I look at here is I have an even power, as I mentioned, and so what I'm going to do here is I'm going to use a double angle formula. And to get myself started, I'm actually going to split it up into two different parts. I'm going to make my integral cos squared x times by cos squared x. And my reason for doing this is I can use my double angle formula and I can actually substitute the values that I've already created here. So this is just rearranging the double angle formula, and I'm going to substitute that straight in. Now the reason for doing that is there is an integral for cos 2x. I can anti-differentiate that. I don't have an integral for cos squared, so I'm creating it turning it into something that I can anti-differentiate. So let's rewrite that using the rearranged double angle formula. It's going to be a half cos 2 theta plus a half times by a half cos 2 theta plus another half. Okay, now I still have a times sign in the middle, so I can't quite anti-differentiate yet, but what I can do is expand these brackets, and I can use my binomial expansion shortcut and make that 1/4 cos squared 2 theta plus 2 times a half cos 2 theta plus 1/4. Okay, so I'm getting closer now to creating an expression that I can anti-differentiate. This second part becomes 2 times a 1/4, which is a half cos 2 theta, and plus 1/4. So what I've got to now is this part of my integral I can anti-differentiate. This part of my integral I can anti-differentiate, but through that expansion I created a squared again. That's a little bit annoying, but I just go through exactly the same process, and once again I'm going to use my double angle formula and substitution. I shouldn't say substitution because we might mix it up with the substitution method, but I'm going to use my double angle formula to turn it into an expression that can be anti-differentiated. So I'm going to have 1/4 times by, now my cos squared I'm going to replace with a half cos, now I have to have 2 theta in here, Now I already had a 2 theta, so when it gets bigger now, it's going to be twice the original angle, which will now become 4 theta. And I just realised that what I shouldn't have done is turn them into thetas. They should still be x's. Plus a half, and then let's keep the rest of our expression. Okay, so now I have created an integral expression that I can anti-differentiate. I'm going to expand the first bracket, becomes 1/8 cos 4x plus 1/8 plus a half cos 2 theta. I've still got thetas in here. Don't know why I've got thetas. Made that mistake before. They just need to all be x's. And you can go back and change all of these other ones up the top here to x's. I just changed my variable halfway through, which is bad mathematics. Plus a quarter. And I can put together an 1/8 and a quarter. 1/8 and 1/4 is 3/8. So my integral expression becomes 1/8 cos 4x plus 1/2 cos 2x plus 3/8. And now I can go straight to the specialist maths formula sheet, and I can anti-differentiate these two expressions. So to do that, I'm going to keep my 1/8 cos of, making mistakes here. Keep my 1/8. The antiderivative of cos is sine. Whatever was in the brackets stays in the brackets, and then I have to divide by whatever the multiple of x was. So I need to divide by 4. Now that's a pretty ugly expression. Rather than dividing by 4, I'm actually just going to multiply it by 1/4. Plus, keep the half. Antiderivative of cos is sine. Keep what was in the brackets, and then whatever the coefficient of x is, I need to divide by. So dividing by 2 is the same as multiplying by 1/2. And then anti-differentiate 3/8 just becomes 3/8x. And then we have a plus c. Tidy up my fractions. I get 1/32 sine 4x plus 1/4 sine 2x plus 3/8 x plus c. And there's my integral for the first part. So let's just recap what were the most important parts. My most important parts were I had an even power, so I split it up into squareds. I used the double angle formula to find a anti-differentiable expression. Okay, let's have a look at our second problem now. So my solution to my second example. So here I have a 3 and a 2. In total, I've got a power of 5. So let me just rewrite that expression so I can remember what I'm working with. Okay, in these problems, when I have an odd power, what I try and create is an expression where I have causes in one part and then a singular sine to the power of 1. And my reason for doing this is because if this part, just trying to get my highlighter, if this part here is kind of the derivative of that, I can do a substitution and say let u equal cos x, and then the derivative of cos x is negative sine x, and I can use that substitution method or change a variable method depending on what you want to call it. My problem at the moment is I still have a sine squared x, and this is where I will often end up using that trig identity cos squared x plus sine squared x equals 1. And that sine squared x, I'm going to rewrite as 1 minus cos squared x. And then I keep that separate singular sine x out the end by itself. So now I can use a change of variable method or the substitution method. Let u equal. Now, I'm not going to make u equal sine because that I don't want to have the derivatives with squareds in it. I'm going to make u equal cos x. So then du dx equals negative sine x. And I can say, well, du or negative du equals sine x dx. So here I'm going to substitute this expression with this expression so they can replace each other. Okay, let's put all of this in. We know, let's get a different colour here. We know that cos x is going to be u. So I've got a cos x here, I've got a cos x here, so I'm going to replace them with u, which becomes a u squared times by 1 minus u squared. And then the sine x dx I'm going to replace with a negative du. So using the substitution method, I've created an expression that is relatively easy to anti-differentiate. Expand the brackets, I get u squared minus u to the power of 4 du. Now note this minus come out the front here. And then I don't like having the minus out the front and minuses on the inside. Let's actually put it all together and make it u to the power of 4 minus u squared du. So I'm just tidying up while I'm in this integral stage to make it as simple as possible. Now this is just a polynomial expression, so polynomials are easy to anti-differentiate. I add 1 to the power, divide by the new power. Add 1 to the power, divide by the new power, and then plus c. The only thing I've got left to do now, substitute u back into the expression. So it becomes cos to the power of 5x divided by 5, or I'm just going to multiply by 1/5, minus 1/3 cos to the power of 3x. And then don't forget your constant of integration, c. And that's the end. So recap, we had an odd power. So for odd powers, I separate my sine and cos and then use the substitution method to help me anti-differentiate. And that's the end of this video.